Hi everyone. In this video, having recently learned a new definition for a limit of a function at a point, and having looked at several examples, we want to briefly review some properties of limits, which may be familiar to you from previous definitions of a limit, as well as begin to explore the concept of continuity given our new definition of a limit. So to begin, I want to remind you we've seen this version of this theorem before about algebra of limits. So if the limit as x approaches a of f of x is equal to L, and if the limit as x approaches a of g of x is equal to m, then essentially these three theorems say that the limit of the sum of two functions is the sum of the limits of each individual function. The limit of the product of two functions is equal to the product of the individual limits. And the limit of the quotient of two functions is equal to the quotient of the limits of each individual function, provided that the limit of the function in the denominator is not zero. Now, these are all definitions that, or sorry, these are all properties of a limit that we observed under our previous definition of a limit, right, under the old definition of the limit. The only thing we really need to be careful about when we try to apply this same theorem for under our new definition of a limit is that we just need to be a little bit careful to think about the fact that we need the value a to be an accumulation point of our domain. However, if you look up here, the fact that we write the limit as x approaches a of f of x is equal to L, that necessarily means that x is an accumulation point of the domain of f. The fact that we write the limit as x approaches a of g of x is equal to m necessarily means that the limit that a is an accumulation point of the domain of g. So then when we go to define these sorts of things, we do not have to worry as much, about whether or not, well, maybe it fails to be a limit point of the domains, right? Because we already, or sorry, an accumulation point, limit point means the same thing, an accumulation point of the domains. So in many respects, the proofs become exactly the same as before. They're exactly the same kind of delta epsilon proofs from before. We're not going to spend time to prove these. Suffice it to say that we can break up limits over sums, products, and quotients just as we have before. The second fact that I'll remind you of, and again, we had a theorem very similar under the old definition of the limit, the sandwich theorem or the squeeze theorem. So here, right, suppose I have a function f of x, which is bounded between two functions g of x and h of x for all x in some open interval containing a, then if the bounding functions g of x and h of x have the same limit at a, so if they are both equal to L, then the function that is squeezed or sandwiched in between them, f of x, must also have the limit L as x approaches a. So this is really just a brief reminder that these theorems that you would have seen in calculus or in an earlier real analysis course or even just earlier in this course all still apply under our new definition of the limit. And again, that's really mostly because this new definition is really just an expanded version of the old definition. It is not a total rethinking. So we should expect that many of the same properties are still going to hold. All right. So now, having looked at that, we now want to go back and consider the definition of continuity, given that we have a new definition for the limit. So let's first remind ourselves that the old definition of continuity of a function at a point was that the function f is continuous at x is equal to a, if and only if the limit as x approaches a of f of x is equal to f of a. Now recall that this really means three things. It means that the limit exists. It means that f of a exists, or said another way, it means that a is in the domain of f. And finally, it means that these two values are equal to each other. So you need the existence of each side and then the equality of the two. So typically in a calculus course, you go through and sort of check these off one by one. Does the limit exist? Is a in the domain? And is the limit as x approaches a of f of x equal to f of a? If so, then that function is continuous. Now, even if we keep this as the definition, given that we have changed our definition of limit, we've also changed this definition of continuity, right? We have expanded the class of functions for which we can talk about the limit as x approaches a of f of x, right? So in particular now, we can talk about functions which are continuous at a point that may not be necessarily defined fully on some open interval containing that point, right? So we just need now that A is an accumulation point of the domain. We actually also need A to be in the domain in order for this to be defined. And then we can check and see whether these two things are equal. So without making any additional changes, we could already see that our definition will have changed slightly solely because we've changed our definition of the limit. Now, to see how this works, let's actually look at a couple of motivating examples here. So the first I want to look back at is actually something we looked at in the previous video. So this is the function square root of x times sine of 1 over x. So now if I look at this function as is, we observed last time that the limit as x approaches 0 of this function was equal to 0. So 0 is an accumulation point of the domain. And we were able to show last time that the limit as x approaches 0 of f of x is equal to 0. Now the question becomes, is this function continuous at 0? Well, very quickly, you can see that, at least as it's stated here, the answer is no. And the reason the answer is no is f of 0 is undefined. 0 is not in the domain of f of x. So immediately here, this answer is no. However, I could make a slight modification. So what if I sort of define my function slightly differently? So I'm going to call this f tilde of x. And I just defined it so that it was square root of x times sine of 1 over x when x is not equal to 0 and 0 when x is equal to 0. Okay. Now, again, notice up here, this actually will not be defined for all x's not equal to 0. So maybe here I should say, x is in the domain of this, delete 0, or just x is in the domain of this, right? But basically, if I came over here and right at 0, right, I sort of imagine I plug in the value 0 there, would this be a continuous function? So now if I think about this, if I consider now here the limit as x approaches 0 of f tilde of x, well, it's going to be the same as the limit as x goes to 0 of f of x, right? Precisely because this function and this function are the same when x is not equal to 0, and that's all the limit actually cares about. Okay, but now f tilde of 0 is defined, right? It is 0, and these two are equal. So this sort of extension, this function f tilde is continuous at x is equal to 0. So we can sort of extend this slightly, this discontinuity in this function that existed at 0 is a removable discontinuity, right? I can just add in 0 there and now create this function f tilde of x, which is continuous at 0. So we see already that, right, under our old definition of continuity, with the old definition of a limit, this would not have been something we could have discussed. However, in this case, we can now see that this function is in fact continuous at 0. All right, looking at another example. Let's consider this function g of x, which is defined to be the square root of the absolute value of x squared minus 1 minus 1. Okay. So this is a little bit of a tricky function if you break to wrap your head around the first time. So if we look at this, this is going to be sort of going to depend on whether x squared minus 1 is greater than 1 or equal to 1, right? Because I need to know, sorry, greater than 1 or less than 1, because I need to know when this thing under the square root is going to be greater than or equal to 0, right? So I need to know when x squared minus 1 is greater than or equal to 0. That occurs when x squared minus 1 is greater than or equal to 1. This occurs when x squared minus 1 is greater than or equal to 1, or when x squared minus 1 is less than or equal to 1. This occurs when x squared is greater than or equal to 2. This occurs when x squared is, uh, sorry, sorry, I was like, something's wrong here. This should be less than or equal to -1, but add 1. This occurs when adding 1 gives me 0. Okay. This occurs only when x is equal to 0. Right? The only way x squared is never less than 0, so it can only be equal to 0. That happens when x is 0. This happens when x is greater than or equal to square root of 2, or when x is less than or equal to negative square root of 2. So you get sort of your domain, right, being these three pieces. So you have uh, all the x values that are greater than the square root of 2. Those are the ones lying over here. You have all the x values that are less than negative square root of 2. Those are the x values lying over here. And then you have x is equal to 0 right here. Okay. And so you've got a plot of this function here. Okay. So now we could wonder, at what x values in the domain of this function do we have continuity? Well, you probably feel pretty good. At any of the x values over here, I have continuity. At any of the x values over here, I have continuity. What about this? What about this point? Now, on the one hand, you probably feel like if you think back to sort of that first sort of definition of continuity you probably learned, which was probably something like, oh, you can draw without lifting your pencil. You go, well, I can't draw that point, right? I can draw this branch without lifting my pencil. I can draw this branch without lifting my pencil, but then I have to come over here to put that dot there. Although just to put that dot down, you don't have to, you just, put the point and then you don't have to lift your pencil off of it. So it's a little unclear what might happen there. Um, if I try to think about, what could I say about the limit at this point? Well, I can't say anything about the limit at this point because 0 is not an accumulation point of my domain, right? So we said my domain here is the set minus infinity to minus square root of 2, union the single point 0, union square root of 2 to infinity. Okay. There's the domain. 0 is not an accumulation point. Okay. Why? Well, come over here. Let me draw a deleted neighborhood. Say this could be the deleted neighborhood of radius 1. So then it would also, right, the deleted neighborhood's going to exclude the point at 0. So this would be like the deleted neighborhood of radius 1 around 0. Right? If I take that set and intersect it with the domain, I get back the empty set, right? This set does not intersect any other point of my domain. So this is the empty set because I have a deleted neighborhood that does not intersect the domain. This is not an accumulation point of the domain. So it makes no sense then to talk about, under our definition, the limit. Now notice that's a little bit different. I'm not saying that, oh, the limit doesn't exist, right? I'm not saying that the limit doesn't exist because we have sort of an epsilon delta issue. I'm just saying we can't even talk about the limit at that point. So under our old definition of continuity, there's also a little bit of gray area because I'm not saying the limit doesn't exist. I'm just saying we can't even apply our definition of the limit of a function at a point to this particular point in the domain. Now, so the question sort of becomes, I mean, in this specific example and more broadly, what do we do with isolated points of the domain? Right? Those are the ones that we're going to have some trouble dealing with that limit on the left-hand side of the definition of continuity. And the response is going to become, we're basically going to just have to make a decision, right? Either we're going to say at an isolated point of the domain, there is, the function is not continuous, or at an isolated point of the domain, a function is continuous. We're going to choose to do the latter. And the reason we're going to do that is twofold. One is if you go back to sort of our sort of an epsilon delta type definition of continuity, usually you say something like for every epsilon greater than 0, there exists a delta greater than 0 such that uh, whenever x minus a is less than delta, f of x minus f of a is less than epsilon. Now, notice that given this sort of isolated point here, right, if my delta is, say, less than 1, okay, then there's only one x value. Normally for continuity, we don't put the 0 over here. We don't have this, right? And the reason we don't have that is because for continuity, I do care what happens when x is equal to a. So there's only one x value that satisfies this. That's x is equal to a. And when x is equal to a, this holds, right? When x is equal to a, you get f of a minus f of a, which is 0, which for every epsilon, 0 is less than epsilon. So the first is that even though it's sort of a trivial case, it's not vacuous, right? There is an x that does satisfy this. And when the x satisfies this condition, then this condition is also satisfied. So even though, again, it's sort of trivial, for isolated points, that does line up that isolated points should be points where our function is continuous. The other reason, which I think is maybe the slightly truer reason, and in fact, it's why sort of that epsilon delta definition comes to be, is that you can actually define continuity of functions even for functions that are, say, less restrictive than being a function from R to R. So you can define continuity for functions from one topological space to another. If you've taken our course in topology, you would have seen this, right? And in there, the definition of continuity is a function is continuous if the preimage of every open set is an open set. Now, here, that basically means if I look at sort of an open set, right, around this point, right, and then I look at its preimage, so the preimage of this would be maybe something that looks roughly, so I look at all the x values that map here. Okay, it's going to be fairly narrow just because of the height of this. So I'm going to come down here. So I'm going to get something like this. And then over here, I'm going to get something like this. And this. Okay. And then I'm going to get the single point right here again. Okay. So I have this sort of strange set that takes the form, like if I'm just drawing the brackets, right? Like, I don't know what the exact values are here. Union, well, I know this is going to be negative square root of 2. I don't know what that point is. This is going to be square root of 2. And I don't know what those points are going to be exactly, right? Those are going to depend on the range here. So the question is, for every open set containing 0, is the preimage of that set an open set in the domain? Now, and you look at this and you go, that's not an open set. Again, in topology, this actually is an open set in the domain using the topology it inherits as a subspace of R. Okay? Now, if those words don't mean anything to you because you haven't taken topology, don't worry about it. But if you have taken topology, right, you can note that this is an open set in the domain using the topology that the domain inherits as a subspace of R. Right? So if you take the open set, let's say I call these points star 1 and star 2, this is star 1, star 2, which is an open set in R, intersect the domain. So this is an open set in the subspace topology that D inherits as a subset of R. All right, so yet again, this is just another reason why we want our function to be continuous at an isolated point. So we're actually going to have to change our definition somehow then to allow that slightly, because this is not a possibility that we'd had to deal with before that we are going to have to deal with now. Um, so looking at our definition of continuity then, and we want to revise it slightly. So let my function f be a function from some set D, the domain, into R, and let A be a point in the domain. Then f is continuous at A if and only if either A is an isolated point of D. So if A is an isolated point of the domain, our function is automatically going to be continuous there. Okay. Or, so let's see, in the other case, if A is not an isolated point of the domain, then it's an accumulation point. If it's an accumulation point, then I can talk about this limit, right? Which still may not exist, but I can at least, use the definition to think about it. And in that case, I'm going to say a function is continuous if the limit as x approaches a of f of x is equal to f of a. Further, and this is really just some terminology, we say a function f is continuous on a subset S of the domain if f is continuous at each point of S. Okay. So the whole idea here for continuity is essentially, let's keep it the same at accumulation points where we can talk about limits. At isolated points, just define it to be continuous. Okay. Again, the reason for this choice is precisely because it conforms to some other definitions of continuity that you may not have seen yet. But again, we want to sort of, as much as we can, if we're going to define continuity for topological functions from a topological space to another topological space, and we're going to define functions from R to R, if we can make them compatible, right, we should. We want to have definitions that are sort of harmonious between different branches of mathematics. All right. To just give one more example of continuity here, sort of now using this terminology, let's think about Thomae's function, which we had looked at again last time. So last time we looked at this function t of x, which it returns 1 over q if x is a rational number expressed in lowest terms, and it returns 0 if x is an irrational number. So last time we noticed that if you can actually take the limit as x approaches a of t of x for every value of a in the interval 0, 1. So said another way, for all a between 0 and 1, the whole domain is 0, 1. It's a closed interval, so every point is an accumulation point. So we can think about that limit. And that limit for every a value is 0. So under our definition of continuity, right, we would say, well, t of x, right, well, it's going to be 1 over q if x is rational. It's going to be 0 if x is not rational. Well, in this case, if x is rational, if x is irrational, then t of x, right, is 0, which is, in fact, the limit as x approaches a of t of x. Oh, sorry. I mean, no, I've said x. I should have said a. So then t of a is 0. So t is continuous. And I'm going to start abbreviating continuous CTS. That's a common abbreviation I'm going to use throughout the rest of the course. So t is continuous at x is equal to a, which is irrational. However, if a is rational, we have a problem because t of a will be 1 over q, right, for some natural number q, and whatever that is, that's not 0, which is the limit as x approaches a of t of x. So t is not continuous at x is equal to a rational value. So again, if we're just looking at this function, I mean, sort of interesting behavior here. You have a function that its limit exists everywhere in the closed interval 0, 1, but it is discontinuous at an infinite number of points in that closed and bounded interval, right? At every rational value in the interval 0, 1, your function is not continuous. However, at every irrational value, it is continuous. These are the sort of functions that kept, I think, mathematicians for much of the 1800s quite twisted in knots. They sort of viewed them as these weird pathological functions, but they sort of they had these definitions that were really nice definitions if you were only dealing with nice continuous things. But then people started to come up with examples like this. So Tomei and Dirichlet and others came up with these sort of horrible functions, at least as they were viewed at that time, that sort of forced people to rewrite their definitions to try and understand how to handle them. All right. Now, falling immediately out of this definition, you get, again, an algebra of continuity theorem. This is, again, because the continuity is defined in terms of the limit, and we have all these properties for the limit, it really all just falls out of that definition. So let f and g be functions from a common domain into R, and let them be continuous at A. Then any constant times that function, a continuous function is continuous. The sum of two continuous functions is continuous. The product of two continuous functions is continuous, and the quotient of two continuous functions is continuous, provided that at that point you're looking at continuity, your denominator function is not zero at that point. Okay, so this again really just says continuity is preserved under all the sort of standard arithmetic operations, right? Multiplication by a scalar, addition, multiplication, division. Subtraction is also technically in here because you can think of that as g plus, or sorry, as f plus negative g. So you would really just apply 1 and 2 to get subtraction. So you can combine two continuous functions in any, nice arithmetic ways, and you'll still get another continuous function. Now, there's one other way we can combine continuous functions, and that is through composition. And what we'd like to say is that the composition of continuous functions is continuous. So that's exactly what theorem 213 here says. So it says let f be a function from A into R, and let g be a function from B into R, where f of A is a subset of B. Okay, so let's first just understand the setup of the functions we have here. So the idea is I'm going to represent R, the set of real numbers, as sort of this blob here. Okay, and I'm going to have three of them. Okay. I have these three blobs, and I have a point. Or sorry, I have some set here A inside R, and my function f maps that over here to some set f of A. Okay. Now I also have a function B. B. See if I can maybe get this blue to show up a little bit. So I have this function G, and G maps from some set B. The set B, and it maps over here, to some G of B. Okay. Now, so again, I have F mapping A into R, and there's its image f of A. I have B mapping from B into R, and there's its image G of B. And the only thing I need here is I want to make sure, because again, I'm going to talk about the composition. So I want to make sure that f of A, for anything I can plug in F, I want to make sure that the output is something that can be plugged into G, right? So this condition that f of A is a subset of B is really just a condition making sure that the image of F is a subset of the domain of G, so that when I define the composition, the domain of the composition can be A also. Okay, so that's the setup here. Then it says, suppose that F is continuous at x is equal to A, and G is continuous at x is equal to f of A. Then we want to show that G composed with F is continuous at x is equal to A. Now, When we go to prove things about continuity now, one of the things we have to consider is that there are two ways to be, there are really two definitions of continuity. There's one for isolated points, and there's one for accumulation points. Now, if we are at an isolated point of the domain, okay, so if A is an isolated point of the domain, then automatically G compose F will be continuous, right? The domain of F and the domain of G composed with F are the same. So if F is continuous at X is equal to A because X is because A is an isolated point of the domain, then it's going to be an isolated point of the domain of G composed with F, and hence it's automatically continuous. So the hard part is what happens when we're at an accumulation point. Okay. To help us there, we're actually first going to prove a short lemma. Okay. And this lemma, so it says if a function G is continuous at A and F is a function such that G composed with F of T is defined and the limit as T approaches T naught of F of T is equal to A, then what this really says is you can push a limit inside of a continuous function. So G is a continuous function, and I'm supposing that this limit exists, okay, and the limit is equal to the point where G is continuous, then I can push this limit inside of the function, okay? This is going to be really helpful to dealing with how do we show that the composition of continuous functions is continuous when we are at an accumulation point. Okay, so we're going to prove this, and then that'll actually make the proof of the theorem quite short. All right, so let's think about how to prove this. Now, overall, when I think about limits, right, of any kind, I'm sort of thinking about, I want to show that if I make inputs close enough, I can make outputs as close as I would like, right? The epsilon tells me how close I need the outputs to be. Okay. So let epsilon greater than 0 be given. Now, in this case, I have two functions. I have f and g. Okay. Now, what I want to first note is that if I can get my f of t's close enough to a, then g of f of t will have to be close to g of a. This is a in this case. Okay. So since g is continuous, at x is equal to a, now I'm going to have a couple of deltas here, and I'm going to sort of code them by which function they go with. So here we're going to say there exists a delta g greater than 0, such that whenever, now in this case, right, just I'm sort of writing down the definition of continuity, whenever x minus a is less than delta g, the absolute value of g of x minus g of a can be made less than epsilon. All right. So that's using the fact that g is continuous at x is equal to a. And notice that again, because I don't have the 0 here, this works whether it is an isolated point or an accumulation point. Okay. If a is an isolated point of the domain of g, then what happens here is a is the only thing that satisfies this condition, and a certainly satisfies this condition, right? So this will work regardless of whether a is an isolated point or an accumulation point. Okay. Now I need to use my facts about f. Okay. So since the limit as t approaches t naught of f of t is equal to a, well, what does that mean? That means I can choose some delta f so that if I get my t's within delta f of t naught, I can get f of t as close as I want to a. So there exists a delta f, oh, sorry, let me say here a delta f greater than 0, such that when t minus t naught is less than delta f, all right, I can make f of t minus a as small as I would like. Now, I don't want to make this less than epsilon. What I want to do here, right, notice that f of t is acting like my input to my function g here. And what this earlier piece tells me is that if I get my inputs for my function g within delta g of each other, then my outputs of the function g will be within epsilon of each other. So what I'm going to do here is I'm going to imagine f of t to be like my x here, and I want to make this less than delta g. Now, I can definitely do this because for any fixed value, this delta g, and sorry, that should be like delta sub g, okay? For any fixed value, delta g, and I've already determined what that is up here, I can choose a delta f such that this holds. Okay, so this is just like taking the place of my epsilon in what it means for this limit to exist. Now, I'm going to sort of substitute back in. So if I take a t value, so if I take a t value such that this is satisfied, then this will be satisfied. But now, again, viewing my f of t like my x here, since these two values are within delta g of one another, g of f of t minus g of a must be less than epsilon. So what have I done? I've shown that for any epsilon, I can choose a delta, in this case it's this delta f, so that if t minus t naught in absolute values is less than delta f, then g composed with f of t minus g of a is less than epsilon. So this means that the limit as t approaches t naught of g of f of t is equal to this value here, g of a. But remember, a was just the name. Let's see, where's here? A is just the name we gave to the limit as t approaches t naught of f of t. And so I have proven the claim as desired here. All right. Well, now that we have that straightened away, let's see how we can put this to use then to prove our main theorem. Actually, I'm going to leave that there and we can just come over here. So looking at this, okay, I'm going to prove this theorem. So let's deal with the easy case first. What if A is an isolated point? If A is an isolated point of the domain A, well, then it just sort of automatically holds, right? Then G compose F is continuous at, right? By definition, a function is always continuous at an isolated point of the domain, no problem. All right, let's deal with the other case then. So what if A is an accumulation point? of A. Well, if A is an accumulation point of A, then given that f is continuous at A, then that must mean that the limit as x approaches A of f of x is equal to A. Okay. Or sorry, is equal to f of A. And then since g is continuous at f of A, all right, now what can we say? We can say that the limit as x approaches A of g of f of x. Now this is where we're going to use our previous theorem here. Okay, so I can push this limit inside of here. So this will be equal to g of the limit as x approaches A of f of x. So in this first step, I'm using the continuity of g at f of A. Now here, I'm using the fact that the limit as x approaches A of f of x, since f is continuous at A and we're at an accumulation point, this has to be equal to f of A. Okay. And so that again gives me then g composed f is continuous at A. See if I can squeeze it at the bottom here. So G compose F is continuous at X is equal to A. Okay. So we sort of do this case by case, right? If A is an isolated point of the domain, then G compose F is automatically continuous at that point. If A is an accumulation point, then we need to use this lemma that we had previously proven to show that. That's where we want to start for today. Next time, we'll begin exploring more properties of continuity. And in particular, what we want to work towards are really understanding those big theorems like intermediate value theorem and extreme value theorem, which help to explain, well, a number of things, but sort of really help us see the impact that continuity has on the behavior of a function. So we will stop this video here and get into that in the next video.